Welcome back, physics fans. What's up? Let's just take a look at what we have next. We have inclined planes. This is going to be lesson 5 on chapter 3.1. It'll be one of the last lessons, and let's take a look at it. Although, if you take a look at the website or the Moodle there, you will see that there is a handout that you could download and follow along. Or you can just screen capture from YouTube and do it the hard way. Example 1, a person is on a ramp standing on a Newton scale and attached to a rope. As the angle of the ramp increases, what happens to the scale reading? The scale reading. Will there be no change? Will it increase or will it decrease? Well, gravity. Without gravity, he'd be just floating around. So the gravity is the big problem, first of all. It's the force, the initial force. Okay, and it's the same force in both of them. So what happens? Think about it for a few seconds. Oh, better not do that. It might be copyrighted. Oh, that's going to be copyrighted too. Some people. Oh, no. Don't want that. Okay. Okay, here we go. As it lifts up, what's happening here? Well, if we went straight up, the rope would have to be holding him and he would be just kind of not even touching the scale. And if we went straight down, then the rope wouldn't even be needed. He would be just standing on the scale. So it goes like he's pushing down heavy on the scale here and not pushing down the heavy here. So it's going to decrease. Explain your physics? Well, it's going to be a distribution of, forces here. And I think, can you consider the same thing, what happens to the rope? Well, the rope is definitely increasing. Okay? Because the sum of the forces still have to equal 0. And the scale here is going to be doing most of the work because the scale is going to be pushing in this direction. But here the scale is going to be pushing in this direction and it can't really do much to countermand that. That has to be this force which is going to be countering it. So the rope is going to be taking on over as it increases. Whoops, too fast. What this shows is that for objects on a ramp, the force of gravity partly pulls the object onto the ramp, squeeze, and partly pulls the object down the ramp, the slide. In terms of the other forces that act on the object on the ramp, there will be a normal force, which by definition is perpendicular to the surface. That's what the word normal means. And if the surface is rough, there will be a frictional force, which is parallel. So, by the way, force of friction is always perpendicular to the normal force. Always. Draw the force diagrams of these questions. Whoops, I'm going way too fast, eh? Ah, Mr. Girl, you can't use a scroll bar yet, can you? Nope, I can't. What did I just click on? I don't know. Maybe I could delete that out, eh? Draw a force diagram for an object on a rough ramp that is sliding down. So it's a rough ramp, so there's there's going to be a friction this way because it's moving this way. There's going to be a normal against the surface, and there's still a force of gravity. And now let's, if it's going up, then the friction has to be down. And then there still has to be a normal, and there still has to be a force of gravity. The force of gravity in the normal, if you just take a look, didn't change, just the direction of the friction did. Draw a force diagram for a mass that is at rest on a ramp. Okay, well, there's still going to be that force of gravity and a normal. But is there going to be friction? Yes, there has to be friction, else it starts sliding. Because if I add these two up, it's going to be a net force in this direction. It has to be in that direction because it's going to slide. If there's no friction on it, it's just going to move in that direction. And if it accelerates in that direction, then the F net has to be in that direction. But we don't want an F net. We want it to be at rest. So there has to be a force in the opposite direction that equals the sum of those two. And that'll be the force of friction. Just so that we add them all up and it's gone. Because the sum of the forces have to equal 0. Okay. Now we're going to have to determine the size. So just take a look at this. In order to determine the size and squeeze of these components, we need to find the angle in the coordinate triangle. Complete the proof below to show that the angle is always equal to the angle ramp. So we need this angle number 4. Okay, we need this, but what is that? Well, we can see that angle 1 is a 90 degrees. The reason? It's a right angle. Or they're perpendicular. Straight down and straight horizontal. Whoops, not there. There. Angle 2. If this is theta, then angle 2 has to be 90 minus theta. Or 180, because the sum of the angles in the triangle, minus 90 minus theta. So this has to be 90 minus theta, because angles in a triangle. Angles in a triangle equal 180. The measures of the angles in the triangle equal 180. What about angle 3? What's angle 3? Well, I can tell you that angle 2 and 4, angle 3. Angle 3 and 2 have to be the same because we've got this is parallel to this. We've got two parallel lines here, and those are alternate interior angles of a transversal. So this also has to equal 90 minus theta, because alternate angles. And if you were cheap, you might have remembered Z angle. And then number 4, angle 4 has to be 90 minus 3. So this has to be 90 minus theta. Well, 90 minus theta is just going to be theta. So angle 4 is equal to theta. Because then again, the reason here, if we had to do a geometric proof, this is the measure of the angles in a triangle must equal 180 degrees. Now, you don't have to remember how to prove it. I just wanted to prove it online and get that done. Since the object on the slope is moving along, it's very important to break up the components of that force in the x direction along the slope and the y direction perpendicular to the slope. So this is the force down, but it's going to move this way. So we need a component this way, perpendicular to the slope. And we need a component parallel to the slope, perpendicular to the slope and parallel. So we need a component down the slope and a component to the slope. Okay? And we're going to set the x direction in the direction of motion because then we want the acceleration to be in one direction. So we can call this the force of gravity. If that's the case, then this is the force of gravity in the y direction, and that's the adjacent. So the FGY will be force of gravity times the cosine of theta, which is equal to mg cosine theta. And this is going to be the opposite, so it'll be the sine. So that's the force of gravity times the sine of theta, which is just going to equal mg sine theta. And those are the ones that we just end up memorizing, putting down onto a formula sheet, is that the gravitational pull is separated into just two components. The component down the slope, mg sine theta, and the component to the slope, mg cosine theta. Sine theta here, cosine theta there. There it is. Your picture had better turned out better than that. So let's try a question. Now let's do it without friction first. Frictionless. 25 degrees, not drawn to scale. That's definitely looking like more like 40 degrees. So draw a force diagram and the gravity component triangle. So the force diagram, the free body diagram, is a normal force and a force of gravity. That's my free body diagram. Now, the force, we're going to have Fgx and Fgy and the normal. Now that's the component triangle, the two different ones. This is not ever drawn in the free body diagram. We never draw the components. But this really helps us. We see that this is the y direction, and they have to balance, and that tells us the normal is equal to mg cosine theta. Oh, goodness gracious, the normal ain't normal anymore. Again, it's not just mg like it was in physics 11. And in here, that's the component that's going to cause the acceleration, and that's mg sine theta. Oh, nice. Find the amount of squeeze and slide components. So the squeeze, if you want, or perpendicular, is 2 times 9.8 times the cosine of 25. And this is going to be 2 times 9.8 times the sine of 25. Okay, well, pull up the calculator. We go 2 times 9.8 times the cosine of 25, and 2 times 9.8 times the sine of 25. And we get the cosine is equal to 17.76 newtons. And the sine one is 8.283 newtons. Deciding to write down 4 sig figs for both. Find the normal force on the mass. We've done it. Find the acceleration of the mass. Ooh, that's going to be a different one. The sum of the forces in the x direction is equal to ma. And we found out that the only one in the x direction is 8. So that's going to be the force of gravity in the x is equal to ma. And that's going to be 8.283 newtons is equal to a 2 kilogram object times a. So a is going to equal that number divided by 2. 4.142 meters per second squared. And the direction of that will be down the slope. Dun, da, da, da. Wow. So if we just took away the slope, it would fall at 9.8 this way. But because it's on a slope, it's going to dilute the gravity. Instead of 9.8, it's only going to go at 4.1. Cool. Next. Well, I think I'd like you to try number 7 ahead of me. This now has friction on it, and it's going to change things a little bit compared to the other one. We did calculate the normal force before. This time it's asking for the frictional force, which is just going to be 0.2 times that normal force. So we've done that. But the acceleration is going to be a frictional force and a gravitational force, and they're going to be in opposite directions. I think it can be done. Try it out, and you'll see it in the next video. Thanks. Subscribe often, like it often, come back often, and comment often down below. Thank you.